Welcome, everybody. Thanks, Emmanuel, for accepting our invitation at CosmoVerse today. Emmanuel is a full professor at the University at the National Observatory of Athens. Emmanuel obtained his PhD in physics at the University of Athens in Greece. Then he was a postdoctoral researcher at the University of Athens, followed by a visiting researcher position at the Institut d'Astrophysique de Paris, France, and Chongqing University, China. He was also an adjunct professor at Baylor University in the US and the Pontificia Universidad Católica Paraíso in Chile. Lately, he was also a visiting professor at the University of Science and Technology in China, and he is co-leader of Workgroup 3 at CosmoVerse. Emmanuel's research into theoretical cosmology involves hundreds of works on modified gravity, including its interface with observational survey data and some uses of machine learning. Today, he will present late-time solutions to the H0 and SA tensions through modified gravity. Emmanuel, you can start, please, when you are ready.
Thank you very much, Jackson and Eleonora, for this nice invitation to give the talk in this CosmoVerse seminars that I think they are well established in these issues. So today I'm going to present some possible solutions to the tensions. Actually, these are just some cases that we want to investigate in order to solve the tensions. However, let me state here that modified gravity is a huge paradigm of new theories, right? So it's not just one particular model or one particular solution. So I want to sketch some possible ways out using modifications of gravity. So let me start. And the basic thing I want you to take back home is the following, that the whole history of astronomy and cosmology, but the whole history of science in general, is a history of tensions between our theoretical predictions and the data. So we observe something, we make some theories in order to explain that. Our theories are perfect in explaining that. However, the advance of technology make it possible to have new observations, more accurate, more precise observations, so new data that put our theories into tensions. So we want to improve or modify or rebuild our theories in order to be able to describe the new data. Then the new theories describe the data until the advance of technology allows for more data that put our theories into tension. So this is the history of science. And of course, I will very briefly show you that this is the history of our astronomy and cosmology. And the question is, in the end of the day, since we live now in the time of tensions, are we approaching new physics? So are we close to a scientific revolution? So let me give you an example how this history goes on. So the first theory of gravity was the Aristotelian theory of gravity, that you know that, for instance, heavier bodies fall faster, and the Earth is the center of the universe. So by symmetry, all bodies fall towards the center. And this was the most lived scientific model in history until detailed observations by Bracher and Kepler, who spent 30 years of their lives in order to map the motion of the planets. So here we have the establishment of heliocenters and the elliptical orbits. At the same time, Galileo was the first guy to perform in a systematic way experiments on gravity. And obviously, he found that all bodies fall with the same speed independently of the weight. Right? So you see, new data put the Aristotelian model into question, and then Newton came and put everything together. As Newton said, the reason that I was able to see in a very, very far distance was because I was sitting in the shoulders of giants, meaning Galileo and Brahe and Kepler. So here, for the first time, we understand that it's the same force that makes planets move and the same force that makes apples fall on Earth, the force of gravity. And actually, for the first time, as humanity, we understood that in order to describe the laws of the stars, so the laws of the cosmos, we need to have a theory of gravity, because gravity is the director of the evolution of the universe, right? So we have Newtonian gravity, and Newtonian gravity works perfectly in the solar system until the advance of technology made it possible to have very accurate and very precise measurements. And in 1859, we observed the anomalies in the perihelion of Mercury. You know, we are talking about a difference of 43 seconds of arc per century. So you can imagine how accurate your observation should be in order to measure that. And people did measure that in 1859. So we have a problem here because this was not consistent with Newtonian gravity. Now, let me sketch you another thing. The tension between the theory and observations, so this Mercury perihelion tension, was discovered in 1859. We know that the solution is general relativity, and general relativity was put forward in 1915. So after 60 years, so 2 generations of physicists lived in the times of tensions, right? So the solution of the tension is not an immediate thing. Similarly, in 1887, we had the Michelson-Morley experiment on the speed of light, which put forward another tension with our theories and the data. And you know that the solution to this tension was special relativity in 1905. So again, for 20 years, people tried to solve the tension. And the solution to the tension, of course, was general relativity. So this is our gravitational theory that gravity is described by the geometry of space-time, and in particular from the curvature of space-time. Very good. Let me mention here 2 things. The majority of people, in order to solve the tensions, believe that Newtonian gravity was correct, but there are extra bodies, so there is extra matter, and particularly there was an extra planet called the Vulcan, which was a planet between the Sun and the Mercury, that in the framework of Newtonian gravity was causing the anomalies in the Mercury's motion. However, the solution to the tension was not an extra planet, so a planet that we had not seen for the moment, so a dark planet in the sense, it was modified gravity. And by the way, the second thing I want you to remember is that general relativity, of course, is the correct answer, but it was not the only trial. Between 1859 and 1915, we had many proposed modified theories of gravity. Of course, in the last 3 decades of the 19th century, we had many trials in modifying the Newtonian law. For instance, proposing an inverse cube law or extended inverse square law, as it was proposed by Newcomb in the 1880s. Also, many good physicists proposed different theories of gravity. For instance, Kelvin, in his theory of everything in the end of the 19th century, or Lorentz, he proposed a theory of gravity based on his ether theory and Maxwell equations. Nostrom actually proposed a different theory of gravity in 1912, actually 2 versions in 1913. Actually, this was the first metric theory of gravity. And even Einstein himself, before general relativity, he proposed a scalar theory of gravity instead of a tensor theory of gravity in 1913. So you see, many people, of course, the majority propose the extra planet, so the extra mass, the extra exotic forms of matter. However, many good physicists proposed a modified gravity theory until Einstein put forward general relativity, right? So we have general relativity, and this is the history of 20th century observations that you are all familiar with it, right? We have the standard model of particle physics, GR, and we have the dark matter sector and everything. So we have our lambda CDM paradigm, which works almost perfectly, right? So this is lambda CDM. Of course, these are the various sectors: dark matter, baryonic matter, radiation, and the cosmological constant. And of course, this describes perfectly the universe at the background level and all the sequence of epochs from inflation to radiation, matter, and late times acceleration. And in general, how we are doing cosmology, of course, you impose homogeneity and isotropy. This is the cosmological principle. We are living in a homogeneous and isotropic universe. So at the background level, we have the Friedman equations, and we make predictions for background-related quantities like the Hubble rate or the density parameters of matter or the equation state parameter of dark energy. And then you go and confront your predictions with various background-related observations from supernova, baryonic acoustic oscillations, CMB parameters, direct Hubble measurements, etc., etc. Now, after you have described your universe at the background level, you go to a more subtle investigation of the universe, examining the perturbations. So you perturbed your gravitational, your geometrical sector, and you perturbed your matter sector, and these two perturbed systems are related through the perturbed field equations. You are all familiar with that. For instance, focusing on scalar perturbations, we are following the standard procedure, and we can define observables like the matter of a density, the growth rate, you know, all this parameterization. This is the growth index, and you can define the observable, this F sigma 8, and actually this actually measures, this is a time-dependent root mean square fluctuations of the linear density. So you have the galaxy distribution, and you calculate their fluctuations within spheres of radius 8 megaparsec. Why 8 megaparsec? In order to be able to be in the linear regime, right? So this is observable, and if you go back, you can relate this perturbation-related observables with your theories, right? The core of your theories. And we know that lambda CDM cosmology is very efficient in describing all the various data sets that are coming both at the background level and at the perturbative level. So this is how we play the game. However, you can see again the same routine. We have a model, we have a paradigm that is very efficient in describing the data, but the advance of technology allows us to make very, very accurate observations that were not possible 20 years ago. Either on Earth, we can build now huge telescopes on Earth with 30 or 40 meters diameter. And of course, now we're living in the space era. We have more than 100 space instruments, space telescopes. And of course, these are our telescopes in National Observatory of Athens. This one is the second largest in Europe. And of course, you're all familiar with the new projects of ESA and NASA and of the Chinese of building huge interferometers on space. So we have the capacity to make very, very, very precise observations, and these observations, again, starts putting our theories into tensions once again. And of course, we have some theoretical problems. For instance, general relativity, which is our theory of gravity, is not renormalizable. So it cannot get quantized through the standard techniques. Of course, we have the cosmological constant problems. We still don't know how to describe inflation. We know the kinematics of inflation, so we know what we need, but we don't have a concrete model. Dark matter sector is also unknown. Still, we're in 2024, and we have no direct indication, direct verification of the existence of dark matter. And of course, something that we in CosmoVerse are familiar with it, we have many, many tensions, large or small tensions between lambda CDM and the data. Of course, H naught and sigma 8 are the most serious ones. But of course, in this review by Leandros and Fotini, you can find many, many other ambiguities or problem or things that need to be careful on that, various anomalies, various spots, various dipoles, various other problems. So you can visit this review to see all of them. And let me mention here that, you see, usually we cosmologists do not care so much about the problem of GR that is not consistent with a quantum description. But this is a serious issue. We should not put that under the carpet. General relativity cannot be quantized. So obviously, it is a low energy approximation, an effective theory of a more fundamental theory of gravity. Otherwise, it could not be consistent to have a quantum matter, so quantum particles, with a classical theory of gravity. The cosmological constant problem is also very serious. Okay, we know that in GR, lambda is just a constant, but in quantum field theory, this is the vacuum energy. So you have a huge contradiction there. So we need to solve that. And concerning observations and cosmology, the most famous tension, of course, is the H naught tension that you are all familiar with it. So it goes like that. If you consider lambda CDM as the underlying paradigm of cosmology, and you take the CMB data, so indirectly, you can estimate a value for H naught by fitting, all the data, and you get one value. However, you can directly measure H naught through the CFIDs and in a model independent way, and you obtain another value. So these two values are in tension in more than 5 sigma. And this is a very serious thing. And actually, although in the beginning we thought that this should be something systematic, as time passes, the error bars get smaller and smaller, and the tension is there, clearly. So, of course, you can propose many models. Many of you have talked on possible solutions on that by assuming extra relativistic spaces, dynamical, dark energy, non-zero curvature, or this is what we will do in this talk, you can propose modified gravity. So you see, qualitatively, a suitably constructed modified gravity will give you less gravitational power, so weaker gravity, and weaker gravity qualitatively means faster expansion. Now, this is the standard transparency that we are doing in H naught discussion. So you are all familiar with that. We have this guy here, and in order to increase H naught, you can follow roughly two ways. The first is to decrease the sound horizon, or you can increase the denominator here, so you can increase this integral. Now, some people call the first direction as early time solution because you change the early time physics, and the second direction, you call it late time solution, right? Now, let me describe here that with modified gravity, you can do both. However, in this talk, I will focus on the second way. So I will modify the late time evolution of the universe. Now, the second tension that you are all familiar with it is the sigma tension. So this is related to the clustering, to the perturbative behavior, and actually the data seems to favor less matter clustering at intermediate scales. Of course, here there is a discussion whether this tension is as serious as the H naught tension, because you can have model dependence in the data, or in various data sets, you can have double counting, so counting the same samples 2 times. However, if this is not systematics, then again, we need to propose a solution, and there are many mechanisms in the literature, reducing, for instance, the rate of clustering at early times, assuming hot dark matter that clusters different as mass scales, or again, modified gravity. Again, qualitatively, if you suitably construct theories of gravity that are correspond to weaker gravity at intermediate scales. Weaker gravity means less clustering because gravity determines the matter clustering, right? So this is how we should move. And of course, you know that you should know, if you are in this cost action, that there are hundreds of solutions of H naught or end sigma A tensions. And to tell you the truth, the fact that we have 100 solutions for the tensions means that we don't have a solution, right? So we are trying to see and study and examine how we should move. And you can find many of the solutions following very, very different paths in this review that many of us here wrote 2 years ago. And of course, in the new white paper that we planned to upload on archive in September, that the CosmoVerse action will put in a paper all possible ways to alleviate the tensions. So here is just concerning H naught tension, the 10 commandments that you should follow in a sense. Of course, you should increase H naught. You should be able to fit all data. And something that usually we forget, you should not murder or worsening the other predictions of the model. So you should not solve H naught tension and get sigma 8 worse, right? And of course, in the end of the day, we should prefer a serious and concrete new theory instead of just a model. Now, qualitatively, and concerning the late time solutions, we should try to obtain new terms in the Friedman equations in order to increase H naught. And concerning, for instance, sigma 8 tension, see, this is the evolution of perturbations under the known assumptions. Again, we should try to decrease that. Here you have two ways to do that, either by changing this friction term, so the background evolution, or you should change the effective gravitational Newton's constant, so the theory of gravity. And you want, in a simultaneous way, to solve the tensions. So, because time is passing, because I will follow the way of modifications of gravity, let me remind you that general relativity was made under some assumptions that you need them in order to obtain theoretical consistency, some assumptions that are completely arbitrary, and some assumptions that are determined by experiments and observations. For instance, diffeomorphism invariance is something that you want it to be there for theoretical consistency. Now, space-time dimensionality equals 4. This is an observationally determined assumption. Okay, we know that according to our range of experiments, we are living in a 4-dimensional world. Okay, but you don't know if this is true at the fundamental level because you cannot go to the Planck scale and make experiments. So you don't know whether space-time dimensionality is 4 or 10. Okay, now the fact that geometry is curvature is an arbitrary assumption of Einstein theory of gravity, right? I will talk on that. The fact that the Lagrangian is linear in the Ricci scalar, so you don't have R squared here, is an assumption of Einstein in order to have second-order field equation. So in this case, Einstein was sure that ghosts and instabilities and the Cauchy problem will not appear. But as you know, the requirement to have second-order field equation is an efficient, but is not a necessary condition for your theory to be consistent. Because the extra, if you do get extra time derivatives in the field equations, perhaps it's not a problem because this corresponds to new degrees of freedom with second-order field equations. This is the case of F of R gravity. So F of R gravity at first appears as a higher derivative theory, so at first appears as problematic, but it's not problematic because the extra derivatives is just the extra degree of freedom with second-order field equation. So this was an assumption by Einstein. That's why Einstein missed F of R gravity. And of course, some other assumptions like the theory to be metric compatible. Again, this is determined by observations. The equivalence principle and Lorentz invariance. Again, there is nothing fundamental with them. Of course, according to our experiments, these are true at the level of the range of applicability of our experiments. We have Lorentz invariance and we have equivalence principle, but nothing is telling you that this is true at the fundamental level. So you can see now that by breaking each one of these assumptions and concrete blocks of GR, you can update theories of gravity. And just to give you another qualitative example, this is the best theory of humanity, the standard model of particle physics that we have the Lagrangians of electromagnetism, weak and strong interactions. So this is the best theory. I mean, you can verify that in the 10th digit of accuracy level, and this is GR. Of course, you can, I mean, our theory of gravity, you can clearly see that this is not the end of the game. I mean, this is a very simple theory. And of course, in the literature, you can find hundreds, if not thousands of papers of modifications of gravity. And I know that many of you here in the audience have worked on that. So you can start from GR and lambda, so from lambda CDM, and you can first add higher order terms in the Lagrangian, like going to Evo-Var, to Lovelock theories, to Gauss-Bonnet theories, to Weyl gravity, etc. You can add scalar or vector or tensor degrees of freedom going to quintessence, to Hordensky theories, to Galilean theories, or to Einstein ether, or to massive gravity and by gravity. You can use higher, you can use more advanced geometries, putting torsion into the game, or non-metricity, or even more advanced geometries like Finsler geometries. You can go to higher dimensions, going to brane war or string theory descriptions of gravity, in which at the fundamental level, space-time is not four-dimensional. So you have many ways to modify gravity. And let me start now from some basic modifications. And at the same time, I will show you, I will sketch how these theories can cure the cosmological tensions. So the first one of the prototypes of modified gravity was the Brans-Dicke scalar tensor theory. So in this theory, you have another extra scalar degree of freedom. And actually, this scalar field determines the evolution of the Newton's constant, right? So we have this scalar field. This is the Klein-Gordon equation for the field. And of course, if you want to be consistent with the solar system data, because this scalar field determines the Newton's constant. Here is the Newton's constant in this theory. This is the scalar field, and this omega is the initial parameter of the model. So this should be very, very large in order for the field evolution to be small, in order for the Newton's constant to be almost constant, according to the data. So in Brans-Dicke cosmology, in the initial version of the theory, we didn't have a potential, but now we call Brans-Dicke theories the one with the potential as well. So these are the Friedmann equations. So you can see that we get extra terms in the right-hand side of the Friedmann equations. And you expect these terms to be able to describe dark energy and also alleviate the H0 tension. So these are the extra terms here. These are the extra terms in the scalar field equation. Matter is conserved. Again, you can choose some potential and describe the dark energy era and the sequence of matter and radiation and dark energy era. And at the same time, you can generalize your theories. Now, in Brans-Dicke theory, we have one extra scalar field. So the Newton's constant is determined by this scalar field. Now, in the 70s, Hordensky asked the following question. What is the most general theory with curvature terms and an extra scalar field with second order field equation? So the consistent theory. And actually, he was able to construct this theory. So Hordensky gravity has 5 terms in the Lagrangian, and you can see that we have, by the way, this is box here, we have a scalar field. Naively, you should think that, okay, this scalar field here will lead to higher order derivatives in the field equations. However, this is suitably constructed with these coefficients in order for the higher order derivatives to kill each other in the Friedman equations. So the Friedman equations are second order. So this is a very good theory, but actually it was forgotten because Hordensky abandoned physics in order to become a painter. And actually he became a good painter. He made a lot of money, but this theory was reinvented, rediscovered in 2008, 2010 in the framework of generalized Galilean theories. So it's the same theory. And now we have our theory, and you can apply that to do cosmology. So in FRW metric, these are the background Friedman equations. So you see you have many new terms of these new functions, and this is the scalar field equation, and you can perturb your theory. These are the perturbation equation, for instance, the scalar perturbations, and you have some conditions. This is the sound speed square, etc., etc. So you have your theory. And just to be complete, some years after, people constructed the beyond Hordensky theories, which are still consistent. But by the way, Hordensky had found the most general theory. So what these people found, actually, in these theories, we have more degrees of freedom, but only one extra degree of freedom is propagating, right? So in Hordensky, we have 2 + 1 degrees of freedom. Here we have 2 + 1 propagating degrees of freedom. Now, how we can solve the tensions? You can clearly see now that we have a huge freedom because we have many unknown functions. So you can adjust your extra functions in order to be able to solve H0 tension. And actually, again, qualitatively, we know that 2 efficient ways in order to solve H0 tension is either to obtain a weaker gravity on suitable scales, or you can obtain a phantom dark energy, again, at suitable scales. Both these directions would lead to an increase of H0. So here, as we saw in some papers, if you consider particular subclasses of this model, you can obtain an effective Newton's constant that is smaller than 1 at particular redshifts, and then it becomes 1. So this modification here can lead to a higher H0. So in Hordensky gravity, you can play with the functions in order to solve the tension because you have a huge freedom. And you can find many papers in the literature by Noemi or other people that playing, for instance, in our model, we didn't play with G3. So in other considerations, you can play with this term here. This is box 5. So this Galilean term makes the job here, and you can obtain H0 equal to 72, or you can have other shift symmetric theories. So you see these functions in principle in Hordensky gravity depend on phi, on the scalar field, and its kinetic energy. Now, if you have dependence only on kinetic energy, it means that your theory is shift symmetric. You can also solve the tensions, and you can at least alleviate it, obtaining higher H0 values. Now, in a similar way, there is another class of modified gravity that you are using in the Lagrangian, apart from the Ricci scalar, nabla R and box R. So you are using these invariants, and if you do carefully the conformal transformation here, you can see that this is a biscalar theory of gravity. So we have 2 + 2 extra degrees of freedom. And if you do a double conformal transformation, you can clearly see that you have chi and phi. So you have 2 fields. And you can use this theory to describe, of course, the matter and dark energy era. And of course, now you can see that since I have a big freedom here, I can choose my theories in order to alleviate the H0 tension. So in these solutions, at the early times, you have a complete coincidence with lambda CDM behavior, and the extra terms become increasing and higher at late times, changing the evolution of the universe. This is the strategy. And there is another class of modifications of gravity, the so-called running vacuum theories. So in these theories, you don't have a Lagrangian, but you assume that the vacuum energy still, it has an equation of state parameter equals to -1, but the energy density is time dependent. It depends on h and h naught, right? So if you have these theories, you can change the evolution of the universe at late time, and you can solve the tension, right? So this is how we are playing the game, and I think I have 15, 20 minutes more. I will mention you now a different way of modifications of gravity. That this is based on changing the geometry. You know that as it was written in the Plato's Academy door, which actually was very near to my house here in Athens, that those that do not know geometry are not allowed to enter. Actually, this is a statement that mentions that geometry is fundamental in understanding nature. Now, let me tell you here, and actually this is a good and bad thing of modified gravity. Modified gravity is a paradigm, right? Is a huge framework of theories, so it's not just a model. And there are infinite modifications of gravity. Even if you exclude through the data an infinite theories of gravity, you will remain with infinite theories of gravity. So actually this is good and bad, but remember, we are living in the tension eras, that people were living in the beginning of the 20th century, and they had many theories in order to solve the Mercury's anomaly, the perihelion of Mercury anomaly, and only one of them was correct, GR. So we're living in the same times. Naively, we investigate many theories of gravity, and we hope one day one class of them to be the correct one. So let me go back to GR. So Einstein, in general relativity, he had the essence of general relativity is that gravity is geometry. Geometry is curvature, so gravity is curvature. Technically, you obtain that by imposing the Levi-Civita connection, which by definition has zero torsion. Now, later on, Einstein had the following idea. He thought that, okay, curvature describes gravity. Torsion could describe electromagnetism. So in geometrical terms, with curvature and torsion, I will have a unification of gravity with electromagnetism. But actually in 1928, he found that torsion does not describe electromagnetism. Torsion is an equivalent way to describe gravity. So in this theory, he called it teleparallel equivalent of GR. Actually, Einstein was not good in names, like in relativity theory. This is because you assume distant parallelism of the vectors. So you impose parallel at the distance. Now, technically, in this theory, you impose the Weinberg connection, which has zero curvature. So gravity is geometry, but geometry is torsion, so gravity is torsion. So we have two equivalent formulations of gravity. And to be more precise, I don't want to get into the details, but just to get the main idea, in principle, you can have three geometrical things. The concept of curvature. So if I have a curvature, then if I parallel transport one vector, then when it comes back here, it has a different angle, and this quantifies the curvature of space-time. I can have torsion. In this case, the parallelograms do not close. So if I move back, right, and then back in the initial state, I cannot close the parallelogram, or I can have non-metricity. In non-metricity, if I parallelly transport a vector, it changes its length, right? So I can have these three quantities. So in principle, I can use whatever I want in order to describe gravity, right? And let me state here that curvature and torsion are properties of the connection, not properties of space-time, right? So if I have a general connection, then I can have both curvature and torsion. If my connection is the Levi-Civita one, it has zero torsion. If my connection is the Weinsberg one, it has zero curvature. You see, curvature and torsion are not properties of the space-time, are properties of the connection. And Einstein, he says in his biography that he was sitting at his desk and he realized that in order to have motion in physics, in geometry, I need to have a connection. So motion is connection. I need to have a rule in order to move a particle or a vector from one point to the next point, right? So you can have many ways to do that. And again, you can define the curvature tensor and the torsion tensor. And by contractions, you can define the curvature scalar, the Ricci scalar, or the torsion scalar. Now, just to give you another motivation, in the 60s, people understood the capabilities and validities of the Gates principle. And in order, we know that this is necessary in order to formulate the theory as a Gates theory and quantize that. And in this procedure, you replace the global symmetries with local ones, and the group generators give rise to the compensating fields. And if you want to quantize your theory, it is these compensating fields that are going to be quantized. So this works perfectly for SU3 cross SU2 cross U1. So for the other three fundamental interactions, and people try to apply that in gravity, and they found that if you follow the same steps, in the end of the day, you need both curvature and torsion. So this is another motivation. And let me just sketch how we're doing calculations here. So the dynamical fields are the tetrad fields or the Waldbein fields, the Vierbein fields. These are the four orthonormal fields on the tangent space. The metric is related to them through this expression. You impose the Weinsberg connection, and then all your information is embedded in the torsion tensor. And by contractions of the torsion tensor, you obtain the torsion scalar, and this is the Lagrangian of your theory. And now you can use this theory to obtain modified gravity. So, for instance, F of T gravity is the first naive case of torsion modification, and these are the field equations, and these are the Friedman equations. What do you observe? That this theory has no curvature equivalent. So you start with two equivalent theories, GR and the telepara equivalent of GR, but if you modify them in the naive way that we are doing in the literature, you obtain different classes of modified gravity. I'm not saying that these are the correct ones and the curvature gravity is wrong, or I'm saying that we are building new theories. So this is F of T gravity. So in these theories, dark energy is of geometrical origin, of torsional origin, and you can use that in order to describe the whole cosmological evolution from inflation to the sequence of epochs and to late time acceleration. And at the background level, you can quantify that and use many models to describe the background related quantities. And of course, you can perturb your theory and examine the evolution of perturbations. Remember, in the modifications of gravity, we obtain an effective Newton's constant. This is crucial for the solution of the tensions. So gravity behaves differently comparing to GR. You can parameterize your models and obtain viable models. And now, what is our strategy? Our strategy to solve the H0 tension is the following. At early times, at the CMB epoch, we want to have complete coincidence with lambda CDM. But at late times, we need to turn on our new torsional terms in order to obtain weaker gravity or effective phantom behavior in order to increase H0. So what we did is that we start from lambda CDM. So we have a torsion scalar plus a constant. This is the cosmological constant. So this is lambda CDM plus a small gravitational correction. But we tune things in order, we suitably choose our functions in order to obtain a higher H0. And concerning the sigma A tension, since in these theories we obtain a different gravitational constant, we want to suitably choose that in order for the perturbation equation to correspond to less clustering, right? So this is what you can do, choosing a quadratic correction. And as you can see, we obtain a weaker gravity. And if you go now and take various data sets from CMB, Bauss, and H naught, you can see that in this framework of F of T gravity, you simultaneously solve H naught tension, so we obtain a higher H naught, and of course, a less clustering. So again, this is just a direction that with this modification of gravity, you could alleviate both tensions. And let me sketch here that, as I told you, one efficient condition is to obtain weaker gravity. So we want the Newton's constant over the standard Newton's constant to be less than 1. This is possible in F of T gravity, but it's not possible in other theories of gravity like curvature gravity. Because in F of R gravity, if you want your theory to be free of ghosts, so if you assume the standard conditions, you obtain stronger gravity. So you see, it's not easy to solve these tensions in this framework in other theories. And let me end in the next 3 minutes, in order to have time for some discussion, about recently constructed theories based on non-metricity. So this is the third simple way to do things: curvature, tonsure, and non-metricity. So in this formulation, I can choose my connection in order to set both curvature and torsion to 0. So all information is embedded in the non-metricity tensor. So this guy is the non-metricity, and I can define the scalar, the non-metricity scalar, and I can use this as the Lagrangian, and then I can use this in order to build modified theories of gravity. Again, the simple theory is equivalent with GR at the level of equation, and equivalent with the telepara equivalent of GR. But if I upgrade that to a general function, I obtain a new class of modifications of gravity with no curvature equivalent. So these are the general equations, these are the Friedman equations at the background level, and these are the perturbations. So I have one theory that changes the background evolution because I have extra terms in the Friedman equations, and also it changes the gravitational strength, right? I think yes, here. So this is the effective Newton constant in this theory. This is the evolution of perturbation. So you see, you can play with your unknown function in order to be able to obtain faster expansion and less clustering. And actually, you can see that these theories are also efficient in solving the tensions. And you can see that there are many papers in the literature that you can obtain a less clustering. By the way, a good advantage of F of Q theory is the following, that there are some classes of your theory that for some particular F of Q forms, your background evolution remains exactly as in lambda CDM cosmology. So you don't change the background evolution, but you change the gravitational constant, so you change the evolution of perturbations. So you can solve the F sigma A tension, even if your background, at the background level, your model is completely the same with lambda CDM. Of course, to be fair, let me tell you here that some of these models may have other problems, like the strong coupling problems or other instabilities. However, since they are efficient in solving the tensions, it's worth it to further investigating them. So let me conclude. The first thing that we need to remember is that the history of science is a constant history of tensions between our theoretical predictions and the new data, right? This is a routine that we have seen that many times in the past. Now, in the 21st century, we have the capability to make a huge amount of observations and experiments. We have really a very big amount of accumulating data, and this data suggests possible tensions between GR and lambda CDM and reality. Now, obviously, we need to change something. So either we should tune things here and there and suggest new small models that are able to provide a way out, or we can follow the history of science and propose new paradigm shifts. So completely new theories that could solve the tensions. Very interestingly enough, we are living in the same situation that people were in the beginning of the 20th century. So some people suggest that we need to modify the universe content. So there are extra fields, extra particles, etc. We can modify the interactions, that there are new interactions, or we can modify the gravitational theory. Let me remind you here that historically, modified gravity has been proven to be the solution quite often, from Aristotelian model to Newtonian gravity to Einstein. So we have a good chance that this should be the solution again this time. And actually, let me end here with this nice cartoon from a Nature Astronomy paper that we wrote with Eleonora and Adam, that actually we are scientists here. You know, this is the Plato cave allegory that we are sitting here. We cannot see what is outside of the cave because we cannot travel in the whole universe. So we just observe things that are coming to us. But from these observations, we need to reconstruct the true nature of things. And many of us, that's why we did this CosmoVerse cost project, many of us believe that the tensions are the way to understand the true nature of things. So by solving the tensions, we will understand in a much better way how the universe works. So thank you very much.
Thank you, Manos. Very good. So a very strong advocate. Any questions? So I'm seeing Pieros. Please unmute.
Hello, everyone. Thank you, Emmanuel, for this nice presentation of several works. I was wondering, you mentioned that according to gravity, there is the curvature. Either we assume that geometry is curvature, so gravity is curvature, or geometry is torsion, so gravity is torsion. And then there is also the non-metricity. And people working on separately in these directions. I guess there are already efforts that they work in combination of all these three, right? Because geometry can be defined by curvature, torsion, and non-metricity at the same time, right? So you can have a combination of those and then construct modifications or extensions of gravity by using combinations, right? Could you please elaborate a bit on that?
Sure. Yeah, very, very good question. Okay, first, let us say that, okay, choosing your geometry doesn't mean that you have a physical theory. You have your kinematics, you have your geometrical tools, but then you need to select your theory. Now, a physical theory, so nature, is a different thing. For instance, Euclidean geometry is a perfect geometry. However, you cannot use that to do physics. So, in the end of the day, you need to see the data. Now, if you have, in principle, you could have both curvature, torsion, and non-metricity or many other things. But remember, in the end of the day, you have to describe the gravitational force, which for the moment has 2 degrees of freedom. So you need to be careful not to put too many unnecessary things. So yes, in principle, you can use all these things simultaneously, but perhaps this is too much. Let me remind you here, because this is something that many people ask. So why Einstein chose Riemannian geometry? Because in 1915, the only non-trivial geometry around was Riemannian geometry. Torsion came into the game in 1919 with the works of Poincaré, Cartan, Weisbach, and the others. So Einstein didn't know about torsion in 1915. When he knew about torsion, then he put torsion into the game. So in the end of the day, there are many geometries around, but you need to be careful when you build physical theories, not to over-describe things.
Thank you very much.
Thank you.
Very good. So, Leandros?
Okay, thank you, Mano, for the very nice and clear talk, which we reviewed lots of interesting points. My point is the following. I want to make a comment on the question. First of all, the reason that Einstein chose curvature and not torsion and perhaps other kinds of approaches to geometry is not only that it was not known there, it's also because the reason it was also nothing else was known there is because curvature is the simplest approach to. So the advantage of general relativity, I think the main advantage is simplicity. It's Occam's razor. If you want to describe the world, you use the simplest approach. So now if you want to go beyond that, there must be some motivation. And this motivation has to come from observation, has to come from something that the observation will tell us, so that we need more parameters. Now, one would say that observations here tell us that we need something else because of the tensions, the growth tension and the Hubble tension. However, these tensions can be explained also without modified gravity, even though I agree that the most interesting and fundamental way to proceed is in fact geometry and modified gravity. However, it's always possible to try to construct some generic challenges, not just to lambda CDM, but to gravity itself. And the key question is, what are the challenges for gravity so far? In fact, to my knowledge, there is no clear direct challenge to general relativity so far. I mean, if you want to write a review challenges for general relativity, it would be more or less empty, because as far as I know, there is no real direct several sigma tension, at least for general relativity direct. So there's no smoking gun signature. Now, the other approach is that if in fact gravity was weaker in the past, as it seems to be needed from these theories to address the growth tension, this would have direct consequences on astrophysics. So if you try, for example, to look at Tully-Fisher relation or other astrophysical properties which depend on gravity, on G effective, and if in fact you had some lower value of G at early times, you would see some signature there. And I'm surprised, in fact, that people have not been trying to look at this possibility to search astrophysical data for these kinds of signatures, because from there you can actually either constrain these changes of modified gravity or somehow verify some signatures. It's interesting that there are very weak signatures, very weak limits on G effective from astrophysical properties, because mostly people have not spent time to check this data. So do you have any suggestions on how to search in astrophysical data for the signatures of the effects that you point out for the growth tension?
Very good, Leandros. Yeah, this is exactly the point and the interesting era that we're living in. That we know, and I will tell you that lambda CDM should be changed and GR should be improved. But if we are doing that in the naive ways that we are doing in the literature, we find all kinds of problems and instabilities or observations and inconsistency. So this is the interesting about our era. Now, I totally agree that at the experimental level, GR has no great problem. GR as a theory of gravity. Of course, cosmology has all these tensions, but again, you can solve these tensions in many other ways. However, the fact that general relativity cannot be quantized is a serious artifact. For the moment, I agree that we don't have an observational inconsistency. For instance, if we observe extra polarizations in gravitational wave observations, this will be a smoking gun of modifications of gravity. But I totally agree with you that changing GR may change many things. That's why in the 10 amendments, I told you that You need to solve some things, but without spoiling all the other successes of the models. And this is the true difficulty. This is the interesting era that we are living in. However, the fact that in principle I'm in favor of modifications of gravity is that because this new paradigm shift can solve you many things simultaneously, like GR did from comparing to Newtonian gravity. Because you see, we can have many other possible solutions, but then your model, I mean, you start doing epicycles. So you have lambda CDM and you impose on it, on top of that, 50 mechanisms in order to solve all these problems. While possible with a modified gravity theory, you can solve all of them. But I totally agree that such a theory does not exist. So for the moment, GR is the most well-fitted theory with the data.
Okay, thank you.
So thank you. So next is Pieros. If anyone else has a question, please raise your hand so you're in the queue. And Manos, also you couldn't share the slides if you'd like.
Yeah. I want to
Pieros,
see
please go ahead.
Regarding the question that gravity is not quantized, then if we see the other way around, quantum physics are described in a flat space-time, and it is successful at the level of special relativity, and people haven't described, well, it's string theory that works on extra dimensions at that level. However, my question is, are there efforts on constructing quantum field theory using curvature, torsion, and non-metricity, either separately or in combination of those?
Yeah. Of course, there are trials. I mean, you can use curvature and torsion in supergravity on other theories, or in string theory, you have all these kind of terms. So in principle, if you want to formulate a quantum field theory of gravity, you should use all these tools. So yes, you can do that. But you mentioned a good comment, because some people saying that, okay, instead of having to extend GR to a very big theory like the standard model of particle physics, let's try to reduce the standard model of particle physics in a very simple equation like GR. Okay, this is the opposite way. People also try that. But you can see the standard model of particle physics is very efficient in describing the data. It's very accurate. So yes, it's quantum. So in principle, you should try to discover a more fundamental theory of gravity, so that GR is just an effective theory, a low energy limit. But yes, all these directions are open in the literature.
Thank you.
Simone?
Thank you very much, Manu, for your talk. My question is regarding one of your last slides when you were talking about cosmological tensions in FQ gravity, and you said something about maintaining the background as lambda CDM and only doing the modifications on the perturbations. Is it a natural thing that the background is the same as lambda CDM, or is something that you impose?
No, very good. Actually, because you can see the Friedman equations here. So if this f of q has square root of q, then this square root of q doesn't appear in the Friedman equations, right? So your Friedman equations are just the original one, the lambda CDM equations. However, the square root of q appears in the perturbation equation. So this is not a general feature of the theory. It's just for particular classes of model that has the square root of q. And many people have studied these terms in the literature.
Good. Because I don't know. I am curious about because usually we see works that keep the the background is lambda CDM, but not like a natural thing or a particular case, like in this one, but something that you are imposing. And I don't know, are we sure that modified gravities can maintain the same background history and change only the perturbations, or do you think we should also consider the modifications on the background and understand the full expansion history?
Actually,
Something in that sense, yeah.
This is just a direction. I mean, you can do that if you want, or you should not do that if you don't want. Some people choose their extra terms in order for the Friedman equations to coincide with lambda CDM and play with them in order to change the perturbation evolution. Some other people can follow both ways. So consider theories that lead to altered background evolution and perturbative evolution. So you can do whatever you want in the end of the day.
Okay, thank you.
Eric?
Hello. Hi. Yeah, I had one quick question, Manos. Just a personal thing, whether you had any preferred FFT or FFT models that you think in particular are fitting the data the best currently. Yeah, that's all.
Okay, good question. You see, I mean, we should not be religious people here. I mean, so let the data, as Leandro said, in order to show us the correct theory. So there are many theories, and we naively investigate many of them. And in the end of the day, of course, confrontation with experiments will show us the correct way. It's like, as one famous guy told, that it's like the following situation. If you know what to cook, you go to the supermarket and you select 3 things and you go and cook it. But if you don't know what to cook, you go to the supermarket and you start buying things randomly, and then you decide that. So for the moment, we are living in the same situation. We know that we need to build a new theory of gravity, but we don't know what the material should be. So for the moment, all the community worldwide, we're just investigating things here and there. And probably sooner or later, the data are going to show us which is the correct way to do that.
Okay, thank you.
Pieros again?
Yeah, a comment on that. So you're saying that the data are going to show us the correct way to do that. However, when you build this particular model of FT, you make the assumption that geometry now is torsion, and this constructs a class of models. However, to be consistent with data, you make some assumptions about what are the particular functions that are needed there so that you are consistent with data. So at that level, we're very subjective, right? So the data can tell us some things, but still it allows a big degrees of freedom how to connect the theory to the data. And maybe we should find a way to discriminate among which functions are necessary to go from the general framework to the particular dataset, right?
Yeah, exactly. That's why it's very crucial to go to completely different data sets. Just to give you an example, Hordensky gravity, I mean, subclasses of it were consistent with all cosmological data, supernova, baryonic acoustic oscillations, CMB, H naught, etc., etc. Okay, so you had many classes of them consistent with the data. And then the multi-messenger astronomy observation came in 1917, which measured that the speed of gravitational waves is equal to the speed of light. So with this one data point, we were able to exclude half of the successful Hordensky gravity models, because in general, in modified theories of gravity, you predict, in general, that your gravitational wave speed is different from the speed of light. So you see, we were doing cosmology, we were doing all kind of confrontation with the data, but one data point from a different kind of observations killed half of our theories. Of course, half of them survived. but this is crucial for all of us to see the importance of new data set. And this is the same for Hordensky gravity in the teleparallel torsional framework that Jackson and collaborators put forward. Again, this is another way of modified gravity. And again, in the end of the day, you need to take this theory and confront it with the data. So you see, this is a combination of theoretical investigation and confrontation with the data.
Thank you.
So we still have many possibilities to apply for grants.
Exactly. Yeah.
So if not, I'd like to thank Manos again for a nice, interesting presentation and discussion afterwards. Thank you.
I thank you very much for the invitation.
Okay, great. So please join us again in a couple of weeks when we have our next speaker, Wendy Friedman. And yeah, have a great day. Thanks so much.